So we are going to see about digital light processing. It is called as DLP. So far, till yesterday, we have seen about LCD and other displays. So now we'll see a digital light processing. These are the various devices you can see for projecting light. You have LCD projectors, LED projectors. So these devices are helpful in projecting light onto a screen. Okay. So how we are going to process these information from coming out of these signals. So what is the input we are going to give and how will the information displayed in the form of light. So that is going to be called as digital light photography, digital light processing. The same way you have something called as digital signal processing. That here we are going to play with light. So it is called as digital light processing. It is called as DLP. So the various devices you can see the different appearance of the various projectors you see in the market and flat panel displays for displaying the light. So the principle of the DLP, digital light processing, is a reflective projection. So I am going to I'm going to project my light onto an object, and from there it will be reflected to form a particular pattern. So you can see here, when you see from outside, it will be like it will be formed directly from this point, but here actually you will be having a reflective you will be having a reflective object which will reflect the light coming from this projector to display these characters D, L, and P. So that is what is shown in the image to you. So you can see fans in a stadium reflecting lights towards the blimp. The light is projected from a spotlight towards fans in the stadium. So when cued by a numbered signal, these fans hold up reflective seat cushion and tilt them away or from a blimp. So fans in this particular section of the stadium, you will have people who will be holding these reflective plates. So when the light is projected onto that area where the fans are sitting with the reflective projected plates, that light will be reflected and it formed at a distant position as whatever they are holding, whatever pattern they are going to hold, that will be formed in the distance position. Okay, that is what is given here. So in the figure A, they say that the fans in a particular stadium are sitting together. They are holding reflective seat cushions, and these seat cushions will tilt the light coming from this projector to some distant point where you can see the projection. By doing so, the fans in the stadium are reflecting pixels of light towards the blimp. The result is that the light pattern is created by the sheet cushion image the surface of the blimp. So this is the what you got. Distance viewer sees the image of blimp. Okay, you can see that is at from a distance. If you see, you can clearly see what is being projected on the distant object. Okay, blimp. This can even be a screen where you can have the projection. So it has to be perfectly planned how the light is getting reflected, and it will be displayed in the screen, which is exactly positioned at this place. It's all based on reflection, loss of reflection. You know, the angle of incidence equal to angle of reflection, right? So everything happens at this angle, the angle of incidence, and how it is reflected back to the blimp. Okay. So the principles of the DLP or DMTD, the projection TV technology can create large screen size at a reasonable price. So we are projecting what you see in the laptop is projected in a huge way. So you can create a large screen size at a very reasonable price. So your laptop may be the configuration, the resolution of your laptop may be small, but what you see on the screen after projection is relatively huge, but you get that as a reasonable cost. Okay. So digital micro mirror device. So DMD is called as a digital micro mirror device, and DLP is digital light processing. So DMD device was in this chip was invented by Larry Holmberg of Texas Instruments in 1987. So what happens? You are going to have an array of 1.3 million microscopic mirrors arranged. So the mirrors are arranged in the form of a matrix, and each mirror is going to occupy only 16 micrometers square, which is almost 1/5 of thickness of a human hair. So each mirror creates one pixel in the projected image. So totally you have 1.3 million pixels. So one mirror is equivalent to one pixel. Pixel, I told you, it is the shortened form of picture element. The pixel is going to project have some information in the form of light. Okay. So here, this DMD device was implemented by Texas Instruments. So it is going to, okay, it is going to measure, it is going to have 1.3 million microscopic mirrors arranged in the form of a matrix, and each mirror is going to be very, very compact, 16 micrometer square. It is only 1/5 of a human hair. So each mirror creates one pixel in the projected image. Okay, it is going to create only one pixel. So this is the animated diagram. So you have several mirrors which are going to be arranged in the form of a matrix, and each mirror will have a display surface which is going to represent one pixel. Okay, it is going to represent one pixel. This is your pixel. The principles of DLP. So micro mirrors can tilt the light source on or away from it. So the micro mirrors, they can tilt the light coming. They can either reflect the light, okay, creating a light or dark projected pixel. Okay, so if the light is tilted to if the light is tilted towards the light source, it is going to be a light pixel. If the light is tilted away from the light source, it is going to be a dark pixel. The light pixel means it is going to be on, dark pixel means it is going to be off. So the bit streamed image can detect the each mirror to switch on and off several thousand times a second. So these pixels, what you have seen, can be turned on and turned off up to see here several thousand times a second. So generally, it is going to be up to 1024 times a second. Okay, so if you see the frequency versus on off determines the gray level up to 1024. So up to 1024 levels of gray levels you can obtain, and you're going to switch it on and off up to 1024 times per second. In 1 second, I'm going to switch it to 1024 times. Okay, so it is going to be on and off simultaneously. Principles of DLP, you see here a color filter wheel is inserted between the light and the DMD. So this is your DMD device. You are going to excite the DMD device by a light source, and based on the configuration of mirrors in your DMD, it is going to reflect the light. That reflected light is going to pass through a color filter wheel. So between the light and the DMD, you have a color filter wheel. By varying the amount of time each individual mirror pixel is on, a full color digital picture is projected onto the screen. So I told you, right? So you can vary the amount of time each individual pixel is on or off by switching them accordingly. So if your switching speed is fast means it will be on and off for a very few seconds. But if you want to increase the switching speed means if it is turning on and off only 500 times on second means the speed is less. So in that case, the mirror is on for a long amount of time. So when you do that way, you can get a full color digital picture projected on the screen. So that is how you get a color image projected on the screen coming from a. Here we, the simplest example, we take the DMD digital mirror disk. We take the example of a DMD. Same thing is here. This is again some more complex, including all other components. You see, you have a DLP board. In that, you have a processor and memory. A processor is there to turn on and turn off or control the characteristics of your DMD. So the DMD is controlled by your processor. So after DMD, you have a sharpening lens to focus the light. Then you have a color filter. I told you this color filter will be helpful in getting a good projection on your screen. Then you have one more lens to broaden your light, and then finally, this is going to be the light source. So this is the light from light source. Light is going to fall on the DMD, and then it is going to be hitting the projection lens, where you can see the in the screen. You can see the display of the image. Okay, so this is relatively the internal block diagram of a DLP unit. So from light source, you will have condensing lens to focus on the color filter. Again, you have a shaping lens to focus on the DMD. From DMD, you will be sending the light to the projection lens, where it will be projecting the image or video on a big, large size screen. So this is the basic operation of a DLP board. So DLP board contains all the equipment to control your DMD. So it will essentially have a DMD plus a processor and a memory. So it the three components of a DLP board are processor, memory, and DMD. Okay. So this is the simple compact equipment which is going to have everything. So you have a DMD, you have a prism, then you have a lens, you have a projection lens system, you have a light funnel, color wheel, and then high output lamp. This high output lamp is going to project your image into the white screen. So prism, this primary lens, and primary lens is going to get the output from the DM, reflected light from the DMD, and it is going to pass that through a light tunnel, then color beam, and then is given as input to your high output lamp. So this lamp is going to project your information. And here from the for the input to the DMD, you will have a light source, you have a prism to focus the light onto the DMD, and it's reflected into the light funnel. So this is somewhat advanced version of your DLP unit. So these websites you can refer to these websites if you need additional information. The LCD versus DLP. So LCD, I'm going to have liquid crystals, which is going to be again in array, but in DLP, I'll be having a micro disk DMD, the digital micro disk. So yeah, I'm going LCD. It will depend on the voltage applied to it. So it will either pass the light completely or it will be opaque to light. But here DMD will reflect the light towards the source or away from the source. Okay, so this is the display you get from LCD and DMD, and you see that DMD is relatively very clear compared to your LCD. So these are the different devices you can have, projectors. This is your conventional projector which we use in education institutions. So this high output lamp will be giving out the it will be giving out the signal to be projected. This is a handheld projector for a little bit smaller projection screen, and this is even more a palm top device which is going to be used for small projections. Nowadays, you can see mobile phones having the facility to project data, right? So same way, depending on the compactness of the device, you can have the projecting capability. So when the size is going to be smaller and smaller, the projection area is also going to be relatively reduced. So this is the different types of projectors we have seen. Now gas plasma display. So the next type of display is going to be gas plasma display. Okay, the plasma, you know, it is a gas made up of free flowing ions and electrons. Okay, plasma is a gas. It is made up of free flowing ions and electrons. The gas plasma display, and it is going to be again a matrixal array of pixels composed of three subpixels, red, green, and blue. You know the primary colors are red, green, and blue. So and you will have cells, and are surrounding these cells, you will be having this inert gases or inactive gases. So then you are going to subject these cells to voltages representing the changing video signal. So depending on what change in voltage you have, you are going to have the changing video signal. So causing the gas to change into plasma state. So generating UV light, which reacts with the phosphor in each subpixel that just generates colored light. So you have a cell. Each cell is going to have three subpixels, red, green, and blue. Surrounding these subpixels, we have what is called as inert gas. And by applying voltage, you are causing the gas to go into plasma state. So plasma is going to be, you are going to have ions charged state, generating UV light. So when the UV light is going to react with the phosphor in each subpixel, you have three basic colors RGB, right? So when the UV is going to react with these subpixels, this is going to generate a colored light. So it is going to generate a multicolored light. So it is going to be emissive rather than transmissive. So it is not going to transmit, it is going to be an emissive type of display. So you see here, the different layers are given. 5 is the address electrode. 1 is going to be the display electrode. 2 is going to be your glass substrate. This is on the front side. 3 is going to be discharge region. 4 is the phosphor. You have RGB. You have, see here, you have red. Here we have green. And here we have the light emitting area. Okay. 5 is the address electrode and 6 is going to be the glass substrate. So between the two glass substrates, you are going to have the three colored regions. Next one, how this gas plasma display is going to work is, so address electrode, which is present here in pi, is going to cause the gas to change to plasma state. So gas in the plasma state react with phosphorus in the discharge region. So here you have the the discharge region where the gas in plasma state will start to react. So reaction causes each subpixel to produce red, green, and blue light. You see here you have red, green, and blue light. This is a single pixel. Depending on the reaction, you will be having the production of red, green, and blue light. And the reaction region is given, discharge region is given by here. Okay. So the same thing is shown in a 3D view. You can see the front and black glass plates. You have a dielectric layer, you have a display electrode, you have a layer, then you have a series of pixels. So each pixel has different coloring, as you see, depending on the phosphorus and the address electrode and protective layers. So you have RGB inside, but depending on how much the gas is converting into plasma and producing phosphor, depending on that much amount of color you can see in the display. So it is a very simple to understand. The only thing you are converting the gas to plasma to produce which will produce UV light when you are going to react with the phosphorus. Okay. So address electrodes sit behind the cells. So address electrodes will be sitting beneath the cells along the rear glass plate in the horizontal road. So after the rear glass plate, you will have the address electrodes, above which you will have the cells. The display electrodes, which are transparent and are mounted above the cell along the front gas plate in vertical column. You see the display electrode is mounted uh, below the front glass plate, along the front glass plate in the vertical column. So display electrode will be at the below the front glass plate, and address electrode will be above the rear glass plate. Like they are very extremely thin, 3 to 6 inches typically, and produce sharp images because they do not use complicated optics and lens assemblies. The gas plasma display is picking up now because it is very thin and produce sharp images and do not use complicated optics and lens assembly. The construction is relatively simple. Images are very bright with high contrast ratios. So we have nearly a 180-degree viewing angle with no light drop off. So even if you view 180 degrees, you can clearly see the pictures or videos. But in LCD and DLP, that is only about 160 degrees. Okay, this difference, additional 20 degrees viewability it is going to provide. So additional 20 degrees of viewability is going to be provided. Technology is highly complex and very expensive. So it is going to be very complex and expensive. Relatively, it is going to be heavy in weight and consumes more power than typical things like LCD, DLP, and CRT. Sometimes require internal cooling fans also. So because producing color light is not that easy, so and conventional projectors after you work with them for a longer amount of time, they become too hot. So immediately you have to switch off them and let them cool. Again, you are for use after some particular break, right? So same way here, this is going to be relatively very heavy, and it is going to consume more power also. And sometimes you require internal cooling fans to dissipate the heat quickly into the environment, because otherwise it would damage your equipment. To damage your equipment. Plasma versus LCD. So we'll see which comparison between gas plasma display versus LCD. The advantage of glass plasma displays over LCDs, viewing angle of plasma is 160 degrees plus 90 degrees vertically, but the viewing angle of LCD is only up to 160 degrees horizontally. No vertical viewing is possible in the LCDs because of the construction of the device. So in plasma, the viewing angle is also very good horizontally, and vertical viewing is also possible from 90 degrees. But in LCDs, only 160, less than 160 degrees horizontal viewing alone is possible. The size of plasma is 32 to 61 inches you can have, but LCD 2 to 28 inches only you can have. Plasma, I told you, it is emissive. Emissive means it is going to emit light because of the reaction. But LCDs are transmissive. Either they allow light to pass through, or they will block the light from passing through them. The switching speed, when you see the plasma have a very high switching speed, less than 20 milliseconds, which is very good for video projection. But for LCDs, it is very large because the crystals cannot adapt to the speed very quickly. quickly. So the image sometimes, if you are displaying video using LCD, there will be, you can see a lag. Lag means from one frame to another frame, the transition, you can see lag or buffering happening in LCDs, which you do not find them in plasma displays. Plasma uses phosphorus, which is a natural TV color, but LCD uses color filters, not the same color system as TV. So technology use is also going to be different. So this is an LCD. This is an LCD display, and this is going to be the, this is your plasma display. Okay, this is your plasma, and this is your LCD. Now plasma was a CRT. So advantage of plasma over regular TV? Conventional TVs, so on that days they were those days they were using only CRTs, right? So it is 4-inch thick and can be hung on the wall, and it is flat panel. Even the CR plasma is going to be a flat panel device, but your CRT, I told you, you will be seeing this big 3D structure on the back of a CRT. So much larger picture can be projected. The color accuracy is very high because I'm going to use phosphors. Brighter images are obtained 3 to 4 times brighter. Better resolution you have better resolution. So better resolution. The high definition capability, HD is also, you can possibly incorporate into this. 16:9 aspect ratio versus standard 4:3. So standard aspect ratio is 4:3, but you can also develop 16:9 aspect ratio, and it can be used as a monitor for PC or Mac. So you can use this plasma displays as a monitor for PC or Mac. Images don't bend at the edge of the screen, so the edges are very sharp, so you can see the image till the edge of your screen, but images don't bend. Reflection from the windows and lights are minimized. Wider viewing angle and not affected by magnetic field. In CRT you have to bend the electrons by using a magnetic field, right? But in plasma displays there is no effect of magnetic field on the display. It is going to work well in a better way. So application advantages of plasma display over projection monitors. The conventional LCD projectors we are going to see. So ideal for any room, even the rooms where space is limited. It is 4-inch thick and can be hung on a wall. So it can be hung on a wall also. Can be used as a monitor for PC or Mac. High color accuracy than most of the conventional projection TV monitors. So because we are going to use phosphors which are going to be used in natural TVs, and I'm going to convert gas into plasma and then project the image, right? So the color accuracy what you get is very, very high. The brighter images than most of the projection TVs, okay? Better television, better resolution than PTVs, wider viewing angle. We told you it is 180-degree horizontal, 90 degrees vertically, not stuck sitting in a sweet spot. So you don't find any point in the display where it is stuck to the same value. No, you can refresh the screen very quickly. So DLP and LCD projectors need bulb replacement every 4 to 5,000 hours. It is cheap initially, but it is expensive in the long run. So you will have a high power bulb inside your DLP and LCD projectors, right? So those bulbs only will ensure projecting the information on a wider screen. So those bulbs have to be replaced every 5,000 hours of running. Initially, investment may look cheaper, but this bulb is the 90% of the cost. So in the long run, it will become proved to be very, very expensive. The next one is LED based system. So this is the example of an LED light emitting diode based display, a very big display you have in a stadium. So LED is light emitting diode, as the short form is LED, the expanded form is light emitting diode. It's a tiny little bulb, small, extremely bright, and uses little power. So you just need to connect an voltage, it will start glowing. And because you have the reaction of electron and hole, because of the electron and hole getting recombined, you have the production of photon. Photon is actually the personification of light. Photon is a particle which represents light. Okay, you do not have a filament here, but you are just illuminating it by the movement of electrons in the semiconductor material. So in a semiconductor, You have a region where you have a lot of electrons. You have a region where you have a lot of holes. By applying proper voltage, you can make the electrons and holes to recombine to produce light. So you don't have filament as you have in the conventional bulbs. No filament to burn out, so they last very long. So close to 10,000 hours, they can easily survive without any problem. So do not get hot at light bulbs too. So conventional incandescent bulbs become very hot, but these LEDs will not be as hot as light bulbs. It is efficient in terms of electricity, because very little amount of energy is wasted on heat. So it is very efficient in terms of electricity. And this is the basics of a diode. So diode is made up of semiconductor materials. It is typically neutral, and I'm going to dope it. So when you dope it, it becomes extra charge. You will have two regions, N and P. N type will have excess of electrons. So N type will have electrons. You'll see here as mentioned, N type has electrons and P type has holes. So initially, when you don't connect anything, it is neutral. But when you connect a voltage, what happens? This N type and P type, uh, some electrons from N type will move to cross and move to P type. Some electron from holes from P type will move to N type, thereby creating what is called as a depletion layer. So this depletion layer is formed because of redistribution of electrons and holes on either side of the device. So diode is actually a sandwiching of N type and P type. So you take an N type and you bond it along with P type. So as soon as you connect N type and P type, this redistribution takes place, forming depletion layer. Okay. I am not applying any voltage here. It happens naturally because of the attraction force between the electrons and holes. So once you have the depletion region formed, you have, I'm going to connect this way. So I'm going to connect the positive of I'm going to connect the P type to a positive of battery and N type negative of battery. Opposite charges are going to repel. So electrons will be repelled by negative charge. Holes will be repelled by positive charge. They tend to move away from the battery. So this helps in crossing the depletion region. So when they cross the depletion region, it gives rise to current. When charges are going to move, you will get the flow of current. Okay, so this is how the diode is work, and this depletion zone will slowly disappear because the force with which the electrons and holes are going to cross is going to be enormous. So the depletion zone, see here how wide it is, and it will slowly start reducing, and then it will become very thin. Okay, so that is what they say here. The depletion layer completely disappears. The free electrons moving across the diode fall into the holes in the p-type layer. So this involves will drop from conduction band to lower orbitals. So the electrons release energy in the form of photons. So it's actually you make them recombine, and you are going to produce the uh, photons. Photons are going to represent your light. So if we have wide energy gap, the spectral frequency of emitted photon is going to be higher. So E is equal to h nu. From Einstein's formula, E is equal to h nu. So if the energy gap is larger, the frequency is also larger. So silicon is going to have a very small gap. So very low frequencies emitted, which is falling in the infrared range. So with silicon made LEDs, you cannot expect them to emit light in the visible spectrum. So they will be emitting light only in the infrared spectrum. So what is there inside an LED bulb? LED, you will see here, you have a diode, and for diode, you have a transparent plastic case to protect your diode, and the terminal pins, positive and negative, for biasing your diode. And depending on the biasing voltage you apply, the electrons and holes recombine and produce light. So it will be coming out in this direction. So it will be coming out in this direction. So we have a plastic bulb which concentrates the lights in a particular direction. So most of the light from the diode bounces off the sides of the bulb, traveling on through the rounded end. So they are confined to the bulb, and they will pass through the circumference of the bulb. Okay, so most of the light is confined. Very few amount of light escape from the LED. An LED based display displays. So LED displays how we are going to form. The basis is going to be having an LED. So you are going to have a LED pixel module. Means it will have 4+ LEDs of RGB. So you have 4+ LEDs of RGB. You see here, red, two red, two green, and one blue. That is how the multiple LED pixel arrangement. So you will have a green, red, blue. So you can have multiples of them also. Okay, you can have multiple number of red, green, and blue LEDs depending on your application. And this is going to be, if you form a fixed pattern, you will have, when you repeat them and the same pattern is repeated, you call it as it becomes an array. It becomes an LED array. So more LEDs you connect, it is going to produce a combined brightness. Okay. The LED displays are made up of the small modules. A single module is shown here. So when you are going to connect this module in repetitive positions, it is going to become an array. A simple example of array is shown here. So several wires run to each LED module. So there are a lot of wires running behind the screen. You see here. So each LED requires voltage to function, right? So you can see several wires running behind the LED screen. Turning on jumbo screen can use lot of power. Yes, so definitely LEDs. When you have multiple number of LEDs in your system, you can see a lot of power consumed by the LED display. Okay, so a lot of power will get consumed because of the LED display. All the LEDs are going to glow. So this is LED display. You have a LED display here. Now we have even more advanced version of LED displays called as OLEDs, organic LED displays. So you have the structure like this. You have metal contact. You have the organic layers. You have organic elements which are going to be present between the contact. Then you have a transparent contact, and then you have the transparent substrate, and from this you get white light. Then you give voltage to the metal content, the transparent contact. Between the two contacts, you give voltage, and according to the organic layers will function in such a way to emit white light. So not only white light, nowadays organic LEDs, you can have any color, any color which is going to be emitted from your. You can, with technology getting developed fast, you can emit any color from the organic LEDs. The electronic device made by placing organic films between the two conductors, anode and cathode. See here, metal, you have between metal contact and transparent contact, you have the organic layers. So when you are going to place organic film, thin organic film between the two conductors, that is going to be called as an organic LED. So when electric current is applied, a bright light is emitted. So this is called as electrophosphorescence. Electrophosphorescence means the effect by which, by producing electric current, I produce phosphorescence effect. Phosphorescence means I generate light. So the electricity is the cause, and phosphorescence is the effect. So by producing by giving a voltage between the cathode and anode, I am going to generate light. So 2 to 10 volt DC voltage I am going to give. You see here, you have a cathode and anode. Between the cathode and anode, you have organic emitters and glass substrate for concentrating the light. And you have two layers, electron transport layer and hole injection layer. You know, when the electrons and holes recombine, you get light, right? So for them to recombine, you have organic layer where the recombination takes place. And this organic emitter, this layer is going to emit light. So electrons from ETL will come to organic emitter. Holes from HIL will come to this layer upon applying the voltage, and they will recombine in the organic layer to emit light. And the organic layers are very, very thin. They can be less than 0.1 millimeters thin. They are very simple to manufacture. So nowadays, polymer organic LEDs can be used, and the organic filter can be quickly and easily applied to the substrate. Sometimes they are available as paint. So we can paint this layer with organic chemicals, which will help in recombination process. Organic structure is very, very simple to fabricate. You see here, you have several cathode lines, you have a polymer layer, and you have a glass substrate, and you have a contact pads. Very simple. And this polymer layer is going to be the organic. This layer will contain lot of organic thin films. Okay, so here you will have a lot of organic thin films. And by proper application of voltage, and the electrons and holes recombination will take place, and you will get a bright light getting emitted from the organic LED display. So no backlight. So you don't have light available at the backlight. The organic LEDs emit light only in the front side. It is very simple to manufacture. Very fast switching time. We told you in LCD the switching time is very less, so it is going to be relatively very slow, and lifetime issues are there. Sometimes these organic uh, films, since you're switching them very fast, sometimes they may worn out very fast. Okay, so the lifetime issues are there with the organic thin film displays. So now the world is moving towards flexible organic light emitting. It is called as FOLED. So instead of glass structures, FOLEDs are made on flexible substrate, transparent plastic to opaque metal foil. So you flexible means you can bend it. It can be bent around the pen. Your pen becomes bright and pen starts becoming light. So flexible means the surface is not rigid. So the surface can be bent. You can wear it as a watch in your hand or like that. So you can be sticking that organic LED into the sides of a pen. So when you apply for some voltage, this pen starts emitting light. Okay, so you can the flexible thin film organic thin films are very transparent, and sometimes they can be opaque. You can make them from transparent plastic sheets or till opaque metal foils. So this one, what you see is a opaque metal foil, and this one is a transparent metal sheet. Okay, plastics are transparent, so you can make transparent things from plastic, and you can make opaque things from metal foils. So Universal Display Corporation, so a passive matrix display was fabricated on a 0.175 thick sheet of plastic. The resolution was 80 dots per inch and 64 levels of gray, and can show full motion video. This was developed by this company. This what you see here. So this is the device showing the video. So the size is only 0.175 thick sheet of plastic. The resolution is 80 dots per inch and 64 levels of gray level. You can even see a full motion video there. So it was invented by Professor Forrest in Princeton University. It is now under development in UDC. This was long back. Maybe this should be commercialized now. More advanced versions would be available for the market. So display technologies for future. So Lumen's Vision Station Projection TV system. So LCD projector has a wide angle lens that projects the image onto hemispherical screen. So you sit before a hemispherical screen. So LCD projector will project the uses a wide angle lens to project the image onto hemispherical screen. So as you see here, you can see that Samsung released an interesting LCD display that folds like a book. So you can fold it, and if you fold it, it will be available as two separate displays. If you keep it straight, it will be like a single TV. It will be like a TV screen, continuous, and have no break here. So yeah, Samsung has released this display 170 into 127 so 17 centimeters into 12.7 centimeters. So it's relatively looking like a TV screen, but it has the foldable feature. So even if you fold it, the working and other properties will not be different. The display of the future, you will have ebooks. Now we have Amazon Kindle, right? So you have ebooks displays for reading your ebooks. So you have all those stuff coming exclusively for reading your books for another purpose. This is only for reading your. You can load the displays with books, and you can use the display exclusively for reading, moving from one page to another, picking up a book from a list of books to be read. So those things are already available. Maybe many more advancements can be expected in the future. So you can see how the display is a little bit big. It is a handheld device. It's looking like a normal textbook, but it is actually an e-book with all the touch and feel features. So you have this micro e-reader ink capsules. So how this e-book is working is e-book is based on e-ink, the reflective technology relying on millions of micro capsules, which are very, very small compared to the human hair. So each capsule contains negatively charged black balls and positively charged white balls. The electric charge determines whether the black or white balls will be at the display level. So you see here, you have positively charged white balls at the top, you have negatively charged black balls at the bottom, and you have a clear fluid. So as and when you apply the voltage, you can see what is getting displayed. So you see here both are positive. So it is like this. Here you see one is positive, one is negative. So near the positive, you have this of half black, and near the negative you have some white. So remaining will be shifted there, and if it is fully minus means you have fully white here and fully black there. So depending on the polarity or voltage you apply, the which ball will be white or black, which will be displayed, that will be determined. If both here, when you see from top, it will be white in color in the first case. When you see in the last case, it is black in color. So when you see in the second case, it is a mixture of white and black, so it represents a gray level. So it represents a gray level. Okay. So it is called as e-ink. Okay. Because you use white and black pigments for display. And so summary of whatever we have seen, to display the projective displays the emissive type, you have CRT and glass plasma. So CRT is going to emit electrons, and electrons are going to hit the positive screen, and you're going to see the picture, right? And gas plasma, same thing. Interaction of conversion of gas into plasma to produce UV. That UV is going to interact and give you light. Transmissive LCD, so it will either allow light or block light. Liquid crystal on silicon LCOS. Reflective displays, you have DLP, which we have seen today. OLED we have seen, and e-book we have seen. So these are the different display technologies we have. So depending on the bit depth, you have the number of colors can be used. If it is 1 bit means you have 2 colors, it is monochrome, black or white. 2 bit means you have 4 colors, it is called as CGA. Okay, 2 bits means you have 2 power 2. Okay, so CGA, color graphics adapter. So CGA is color graphics adapter. 4 bit means you're going to have EGA. EGA means extended enhanced graphics adapter. So 8-bit means you have 256. It is called as VGA. You know what is VGA? Video graphics array. Okay. And 16-bit means you're going to have 65,536. That is called as XGA. XGA means it is going to be enhanced. XGA is extended or enhanced graphics array. Then we have 64-bit means you'll have 16 lakhs 70, say 777 216 colors. It is called as SVGA. Okay. So SVGA display means is SVGA, it is Super VGA, Super Video Graphics Adapter. And finally, you have 32-bit depth means you have 16 same thing, plus you have some alpha channel for enhancing your display. So as the number of bits increase, the number of colors which you can definitely project onto your screen is also going to be increasing. So your picture becomes more and more clear. Complexity is also going to increase. The cost is also going to increase. Okay, so that is the displays we have seen. So one more topic I think it is left, which is called as graphics display. I think we can see it in the tomorrow's class.